A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians! Welcome back to another video! Will you please take a look at the clock? It's 8 AM in the morning and I'm already recording videos. I'm such a beast. Even before going to work at school, I'm already recording videos. It's quite an exciting video for me because we are going to solve one of the not so many non-linear differential equations that you can find and that you are probably familiar with, that you have seen before. We are going to solve the equation for the undamped pendulum exactly today. It's going to be quite exciting and it's going to involve a special function which we are going to go into more detail in another episode. But we can actually solve this thing and this is pretty brilliant, just like our sponsor Brilliant. Please check the link out, you can support the channel this way. And now we are going to dive right in, not gonna waste any more time talking. We want to solve this boy right here. And no, we are not going to say let phi be really small, basically I'm really small. No, we are going to go through the whole process of solving this nonlinear differential equation of the second order. And for this I would like to make use of a trick at first that I have used before when deriving the conservation of energy before my analytical mechanics playlist. You can find the link down there in the description. Namely, I would like to multiply both sides by a non-zero angular velocity. Meaning, what we are going to do is we are going to multiply both sides by phi dot. Meaning we are going to end up with phi double dot times phi dot plus g divided by L, so pi squared divided by L, times the sine of phi times phi dot, being hence nothing but 0. Okay, this is what we are having now, and you might ask yourself, how does this help Papa? Well, using this very sophisticated trick, we can actually reduce the order of differential equations, which is going to come in really handy overall. I want you guys to notice something. Phi is always time dependent. So if we were to use the time derivative on, let's say, phi dot squared, okay, let's just take a look at an example. Phi dot with respect to t. If we were to use the time derivative on its squared part, what are we going to get? We need to make use of the chain rule because our phi is with respect to t. Meaning at first we are going to drag the 2 down, that's the power rule. We are going to end up with 2 times phi dot with respect to t, but also we need to take the inner derivative. Phi dot differentiate with respect to time is going to end up with phi double dot. This is good. You might notice something. Phi double dot times phi, which we have here, is hence nothing but 1/2 times the time derivative of phi dot squared. Meaning this thing right here, okay, you don't need to take the partial derivative, I'm just doing so because it's less writing. This thing right here is nothing but phi dot squared over 2 but the time derivative of that thing. That is cool, right? I mean, with this little method we can actually reduce the order. We turn this second order nonlinear differential equation already into a first order one. Now all that's really left to do is to take a look at this thing right here, and it's pretty similar actually. If you go through the same process, you might notice that what we have up here is nothing but the time derivative of negative the cosine of phi. It does make sense if you think about it. If you differentiate the cosine with respect to t, okay, we are at first going to differentiate the cosine with respect to phi. Okay, leaving us with negative the sine. Negative and negative is going to cancel out, going to become positive. Okay, we're going to get positive the sine up here, this is good. Also we need to take the inner derivative, and phi differentiate with respect to t is just phi dot. And this is good. So meaning overall, what we are going to end up with is nothing but the differential, okay, let's use the partial differential, really doesn't matter, of time. We can drag this linear operator to the outside, okay, just using the linearity of the operator. Phi dot squared over 2 minus and then g divided by L times the cosine of our boy phi, and this is nothing but 0. And now you can go ahead and basically integrate both sides with respect to t, or you might notice something. If you differentiate something and it's going to be 0, then that means that something you differentiated is nothing but a constant. Meaning what we can conclude from this right here, just like with the conservation of energy that I have derived before from basic conservative forces and conservative potentials, we can actually notice that phi squared over 2 minus g divided by L times the cosine of phi is hence nothing but some constant c. I don't care. And what we can also do is we can multiply both sides by 2 because it's not equal to 0, because it's successor of 1. Okay, we're going to get 2c right here, and 2 times a constant is yet another constant. We are going to call this thing capital C. Really doesn't matter. Also, 2 times gravitational acceleration over the length of the pendulum is yet another constant, but this thing actually has dimensions, so that's something you need to take into consideration later. We're going to give this thing the name, I don't care, small k for now, really doesn't matter. Okay, now we have a first order nonlinear differential equation, and now we are going to play around with initial conditions that we have defined when actually going through the process of getting the differential equation of our simple undamped pendulum. So at first I want you guys to notice if we displace a pendulum at first, so if you want to swing a pendulum, just like with my Newton's cradle that I'm having here, you can get those on stem merge. It has an initial displacement, okay? And the initial displacement goes right down there to Earth, okay? And you can actually read the angle there in some way. Meaning we have an initial displacement, and in the last episode where we applied Laplace transform to the reduced differential equation with the small angle here, we said that this initial displacement was nothing but some phi naught. Okay, this right here is just some simple phase shift that we are having at first. Meaning, if we take a look at the angle phi at the point t being equal to 0, so phi of 0, we are going to notice that this is nothing but our initial displacement, phi naught. But before we start the pendulum swinging, what is its initial angular velocity? Well, it's 0 obviously. I'm not letting go of this thing. Now it has an angular velocity, but before it really didn't. Meaning our phi dot at the point t being equal to 0 is 0. And this comes in quite handy actually, because if we were to plug in those initial conditions into here, you might notice that phi dot of 0 squared is going to be 0, leaving us, by applying the initial conditions, with nothing but negative k times, and now we are going to get the cosine of phi of 0 is nothing but phi naught, being hence nothing but our constant c. Hey, this is pretty good, right? I mean, we have found out our constant c with just physical interpretation, which is really good if you ask me. Meaning overall, our differential equation is going to turn into phi dot squared minus k times the cosine of phi, being hence nothing but, well, our negative k times the cosine of phi naught. And this is what we are having up until now. What I want to do now is I would like to separate this equation to just have phi dot on the side. We're going to play around with the expression a tiny little bit. At first I would like to add k times the cosine of phi on both sides, meaning getting rid of the equal sign and putting it here. Okay, this is what we are having right now, and also you might notice that we are going to have a common factor of k here on both terms, meaning we can also factor this out. This is why I love chalkboards. You can just erase everything and turn something into another something. And that's what we're having now. To manipulate this, we need to make use of the double angle formula for the cosine. It just comes in really handy because stuff is going to cancel out, and it's going to make argumentations a tiny little bit easier on the upper and lower bounds later when integrating with respect to the initial conditions. So now we are going to take a look at the double angle formula for the cosine. I want you guys to remember that the cosine of phi is nothing but, I mean, we can expand this by 2 over 2 basically. So that's the cosine of 2 phi over 2. Well, this right here is the double angle formula for the cosine. On the one hand, it's going to turn out to be the cosine squared of phi over 2 minus the sine squared of phi over 2, but you can equivalently rewrite this as 1 minus 2 times the sine squared of phi over 2. I'm not going to go into too much detail here because this is pretty trivial and I have used this extensively before and derived it before, etc. Meaning on the one hand we have that the cosine of phi is nothing but 1 minus 2 times the sine squared of phi over 2, but we can also do the same spiel here with the phi naught, just plugging the phi naught into the place where the phi is here. Meaning our phi dot squared is going to end up to be k times, okay, we're going to get 1 minus the sine, 2 times the sine squared of phi over 2, and then minus 1, you see, the 1 and negative 1 is going to cancel out, and negative is going to become positive. Positive 2 times the sine squared of phi naught over 2. Now you might also notice that we have a 2 here, which is a common factor. We can bring it to the outside. Let's bring the 2 to the front. And well, 2 times some constant k is nothing but, I don't care. It's a constant kappa, for example, or it's a, no, let's go for a constant r. Okay, leaving us overall with phi dot squared being equal to r times, okay, switching the order here because addition is commutative, you might know this, sine squared of phi naught over 2 minus the sine squared of phi over 2. Okay, great. Now we got this right here. Also, you might notice something completely different. We have a bunch of constants flying around here because if we just plug in the initial value, it's not dependent with respect to phi anymore, meaning sine squared of this is just another constant. For substitution's sake, when solving the differential equation, we are going to say let just the sine of phi naught over 2 be equal to some constant k. Meaning this right here is going to turn into k squared. You are going to see why I did this exact substitution in a second. It's going to come in quite handy. Also, what we are going to do is we are now going to take the third on both sides, the square root, just taking a look at the positive branch, because you can get negative values out if you just have a negative angle at first. So instead of a displacement like this, you can say, okay, let us have a displacement like this, and you're going to get your negative sign in the process. This is really not a problem. If you do theoretical physics, you don't care about the signs at all. You just say at the end, well, our physical system was negative to begin with, negative displacement. Well, now we got our negative solutions. That's great. So taking the square root on both sides, we are going to get the square root of r, and also we are going to get the square root of our k squared minus sine squared of phi over 2. And now we actually came pretty far. Now we got a nice separated differential equation where we can divide both sides by this part. Under the condition that it's not equal to 0, we are going to suppose that it's not equal to 0, leaving us overall with phi dot divided by the square root of k squared minus sine squared of phi over 2, being hence nothing but our square root of our constant r, where r is nothing but 2 times k, and k is nothing but our g divided by l times 2. Okay, this is what we are having now, and now we can actually go ahead and solve our differential equation after doing so many manipulations. Really reminds me of my boy Coxetter's integral. We can start doing integration on this thing. What are we going to integrate with respect to? We are going to integrate with respect to t on both sides, because you might notice that phi dot is nothing but phi differentiate with respect to t, and the dt over dt is kind of going to cancel out, like the physicists would say, meaning integrating with respect to t is the right choice here. I mean, it's a time-dependent system, so it does make sense to integrate with respect to time in some way. We want to get from phi dot back to phi, to just our angle. Meaning we are going to integrate with respect to t, also this part right here, but we don't just want to integrate with respect to t because we are going to get a constant out this way. We want to integrate with respect to our initial conditions. And this is really not too hard. I'm going to erase some stuff and then I'm going to see you on the next blackboard. So after writing everything out, we can get to the grande finale. So at first I want to get rid of the dt here. You can get rid of the dt formally by doing just a simple substitution with a new angle basically. But we are going to play physicist and say that dt over dt is going to cancel out in the process. I have made so many videos on differential equations before, showing you the process of cancelling out the differentials rigorously. Just take a look at the whole differential equation playlist. You're going to see that everything's in there. So we are going to end up with just d phi up here at the top, and the dt is going to cancel out. And this is basically it. Now I told you that we would like to integrate with respect to initial conditions, because then our pendulum is going to be solved as being an initial value problem basically. So I would like to concentrate on the left-hand side at first, because it's actually quite clear if you integrate with respect to phi what the initial conditions should be. We really don't have too many givens. At first we are going to have like no displacement at all, and up until our initial displacement, which is going to be the highest point of the amplitude, we are going to integrate. Those are the only real initial conditions that we have. We don't have an angle phi if it's just hanging down parallel to Earth, not parallel, perpendicular basically, but also we have this initial condition given that phi at the point t being equal to 0 is nothing but phi naught, meaning we are going to integrate from 0 to phi naught, and the same thing here. Now this might seem really weird, integrating with respect to time from 0 to phi naught, but let's take a look at this from a physical point of view, because what we have here basically is the situation that we displaced our pendulum and we're integrating from 0, this is this position, up until phi naught. You might have heard of the period time before. The period time is the time it takes for a pendulum, for example for an oscillator, to go from left to right and right to left once. Now, what is the period time from 0 to our initial displacement phi naught? Well, we are going from here to there. This is just 1/4 of our period time if you think about it. I mean, going from here to there is just 1/4 because we need to do this process 3 times to get to 1 period time overall. So integrating this from 0 to phi naught is going to result in the period time, capital T, over 4. It actually makes sense if you think about it for a second. Okay, this is what we are having now, and now we can start to integrate what we have here. And for this I would like to introduce a substitution that is pretty similar to the substitutions I have introduced on Coxetter's integral. Like I said, it's pretty similar actually in so many ways. I don't know why, but it just happens because we have square rooty stuff of, of trigonometric stuff. So we are going to introduce the absolutely naturally incoming substitution. Let our sine of phi over 2 be nothing but, okay, we want to get rid of this part right here, but we also want to factor out our k squared in some way right here. So if we were to square our sine of phi over 2, we want to get something with k out on the other side, because this way we can factor out the k squared on both terms and taking the square root of that. But also we would like to introduce a new sine wave with respect to an angle var theta. This thing right here is a theta, it's a var theta. Okay, this is what we're having now, and we can start doing implicit differentiation, meaning we are going to differentiate this with respect to phi and this with respect to theta on this side. Well, on this side we are going to just differentiate it. We are going to get the cosine of phi over 2, but also we need to use the chain rule. We need to take the inner derivative with respect to phi, which is just 1/2, leaving us with 1/2 times the cosine of phi over 2 times d phi, being nothing but, okay, and this side is pretty trivial, k is just a constant, then we are going to get the cosine of theta times d theta. Doesn't look good, right? I mean, we still have cosine of phi over 2 here. But it's not a problem if we take a look at Papa Pythagoras, okay, fundamental theorem of trigonometry. We know that sine squared plus cosine squared is equal to 1. We can subtract sine squared on both sides, so cosine squared is nothing but 1 minus the sine squared. And now we can take the square root on both sides. Our square root is going to be positive just because our angular displacement is going to be positive. We assume that it is. Meaning overall this part right here is going to result in the relationship that this is nothing but the square root of 1 minus the sine squared of, and now phi over 2 is the argument right here. And that's pretty good if you ask me, because sine squared of phi over 2 is nothing but k times the sine of theta. So this part is actually the square root of 1 minus k squared times the sine of theta, but squared. Okay, good stuff. We now know what d phi is. We can divide both sides by this and multiply both sides by 2, because not equal to 0 is the successor of 1, meaning d phi is hence nothing but this horrible expression. It's going to be 2 times k times the cosine of theta divided by, and now we are going to get this part, square root of 1 minus k squared sine squared of theta. But it's only looking horrible at the surface right now. It's actually not that bad. We're now going to plug the substitution in. We are going to notice that square root of r divided by 4 times t is hence nothing but an integral from, what is the integral going to be exactly? I mean, we have to plug 0 and phi naught into here. If you plug 0 into phi, that's kind of trivial, it's going to be 0. K is not equal to 0 because k has been defined like this. That's a little hint. And our angular displacement was assumed to be non-zero, otherwise everything would just be 0. That wouldn't make any sense, right? So meaning that's non-zero, meaning sine of theta must be equal to 0, meaning theta overall must also be 0 on the principal branch of the sine. Okay, meaning 0 is the lower bound, but also we can plug our k into here, our value for k, leaving us overall with, I'm going to put this here. We are going to have now that the sine, and we need to plug in our phi naught, this is important. Sine of phi naught in the substitution is hence nothing but sine of phi naught over 2 times the sine of theta. You might notice something. It's not equal to 0. This is what we assume. We can divide both sides by it. Meaning sine of theta must hence be equal to 1, and this happens on the principal branch if we are at pi over 2, meaning theta must be pi over 2. And this is good. Now we found our upper bound. Okay, pretty easy argumentation if you ask me. Now we can plug everything that we have into this boy right here, meaning we are going to have that d phi is nothing but this horrible piece of junk that we're having here, but also we are going to have 1 over, we are going to have the square root of k squared minus, and sine squared of phi over 2 is nothing but k squared times the sine squared of theta, which is actually not even half bad. We can factor out the k squared on here, take the square root. So this right here is going to turn into 1 over k times the square root of 1 minus the sine squared of theta. But this might also seem pretty familiar to you because we have used this before. This is the same relationship that we have here, meaning this tiny little part that we're having here is nothing but the cosine of theta. Pretty ingenious, right? The substitution, I love it. It just works wonders. And now overall what we can do is we can just plug in our d phi, this last thing that's missing, meaning we are going to get 2 times k times the cosine of theta divided by the square root of 1 minus k squared sine squared of theta. And all of this integrate with respect to theta. Okay, that's a huge mess that we're having here, but it's not even half bad. It's actually pretty good. You might notice something. We have, this right here was the absolute k, or the absolute value of k, but we assume phi naught to be positive, so our sign is also positive in this range, okay? Meaning our k and 1 over k is going to cancel out, also cosine of theta and cosine of theta is going to cancel out, leaving us overall with, if we were to multiply both sides by the reciprocal of square root of r over 4, we are going to get that the period time t is nothing but 4 divided by the square root of r. And now what we are going to get is the integral from 0 to pi over 2 of, and all that's really left is, okay, we are going to have a factor of 2 here. We can bring it to the outside, turning the 4 into an 8. Also we are going to have our d theta divided by the square root of 1 minus k squared times the sine squared of theta. And now we are done. Solution to our differential equation. Doesn't seem like we are done, right? Because we still have this thing right here. But this thing is what you call in higher mathematics the complete elliptic integral of the first kind. And this is what it is. I'm going to denote it in a second, what it's basically looking like with letters and shit. But I would also like to substitute our square root of r in. So r was nothing but our 4 times g divided by L. If we take the square root here, positive stir, we are going to get a 2 out here and square root of g over L. Meaning if we were to take the reciprocal, we are going to get 1/2 times the square root of L over g. Meaning by plugging everything into here, final solution is going to be the period time of this system, which is the most important part, can be described as being the following. It's going to be, okay, 8, and our 2 is going to cancel out to being just a 4. 4 times square root of L over g times the complete elliptic integral of the first kind, which is being denoted by k of, and well, this thing right here is just an integral. It's not with respect to theta, not with respect to the angle that we had, but it's with respect to k. It's parameterized in our small k, k of k, kk, okay, and hence we are done. This is really exciting to me, and I just love this thing. If you got any more questions, please leave the comments down below. Keep them coming, I'll try to reply to you. Yeah, and this is how you can actually calculate the period time, and in some of the next videos I'm actually going to give you an approximation for this k, or an exact approximation you could say, Taylor series expansion for this integral, which is going to be quite exciting. But before we end the video, I would like to thank today's sponsor Brilliant for sponsoring yet another episode here on this channel, and I for myself was pretty excited that they decided to sponsor this video because it's just really dear to my heart. I just love elliptic integrals, and I couldn't wait to introduce it to you guys here on this channel, finally. I know I'm not doing too much physics on this channel normally, but that time is over. Doing more physics starting from this point onwards. I studied physics, so I'm bound to do some more content on this regard here on this channel. Over the course of this video you might have noticed that really simple physical models like a simple pendulum could turn into something really horrible like this nonlinear differential equation that is extremely hard to describe using mathematical terms. But we were able to do so, and I'm really glad about it. And like with all experimental physics, it takes quite some effort translating our real-world models into the language of physics and mathematics. And the best way for you to strengthen the skill is by practicing over and over again. Grab yourself, for example, a ball rolling down an inclined plane and start formalizing the process. One very cool way to do so is by using Brilliant, who were kind enough to sponsor this video. Brilliant is an online learning platform and app with a huge repertoire of all scientific topics and exercises you could possibly think of. Be it classical, Lagrangian quantum mechanics, or even mathematics. By practicing and thus going through an active learning process, you get the chance to max out all your scientific skills. So if you're like me and love learning new stuff and practicing through various exercises, you should make sure to try them out. So if this feels like something for you, if you think that Brilliant could benefit you in any way, then make sure to check out the link at the top of the description. With it, you're going to get free access to a big portion of Brilliant already, and the first 200 people to actually use the link get 20% off an annual premium subscription, which is a freaking great deal considering how much stuff they have on their website already. Nearly 70 interactive courses, which is just absolutely brilliant, just like the name would suggest. So check it out and support the channel this way. Other than that, I hope you did enjoy this video. If you did, please like, subscribe and comment, channel flag. Don't forget to check out STEM Merge too, talking about nonlinear differential equations. Take a look at our nonlinear collection. Okay, we got a bunch of stuff. Also, the trivial merge is going to be 10% off the whole collection over the course of this week, STEM week this time. And yeah, subscribe to Flammy Maps. Tune out in the next video. Have a Flammy day. Ciao.